Okay, we are now recording, so it's over to you, Giandomenico.
Yes, so it's a great pleasure to have today Zlatko Papic from University of Leeds. So he's an associate professor and he's a leading expert in the fractional quantum Hall effect and many-body localization of quantum scars. And today he's going to talk about non-equilibrium dynamics of fractional quantum Hall states. So I will switch. No.
Okay, so some echo.
It's a mute, no?
Is it mine? No.
Where should we? It's the microphone is low, right?
But the sound.
Yeah.
It's a bit Star Wars.
Wait.
Yeah. Looks
Yeah.
like.
Okay.
You can still hear me, right?
Yes.
Okay. Very
Yes,
good.
we can hear you, yes.
All right. Okay, thanks, Giandomenico, for the introduction. Thanks for everybody for showing up. So yes, today I would like to tell you about non-equilibrium dynamics of fractional quantum Hall states, which is, some things that we've been thinking about in the last couple of years, which is sort of bringing together this, field of topological phases of matter with the field of quantum dynamics, which people usually study, like cold atom systems and things like this, because that's what they can do. And topological phases, on the other hand, are mostly studied in solid state systems. So it's a kind of blend of these two different topics. So this is basically a historical timeline of different kind of quantum Hall effects. And well, probably most of you are roughly familiar with this history, but basically it all started, the first works on this topic are related to these now quite old papers about the idea of particle statistics in 2 dimensions, which slightly predated, the first experimental discoveries, first the integer quantum Hall effect and then the fractional quantum Hall effect, where people discovered these unusual phases of electrons in 2 dimensions where, particles can have this strange idea of statistics, which is different from fermions and bosons. And as you see here, there's lots of interesting, this field has been extremely rich. So it produced all kinds of, interesting concepts that are now broadly used throughout physics. Things like anyons, topological order, non-abelian excitations, non-abelian statistics. And of course, it's still very much an active subject. There's lots of quite recent experiments with these new materials like topological insulators, graphene, and then, various kinds of one-dimensional systems, which captures, some aspects of all this interesting physics. As you see, it was also quite lucrative for people who worked on this. There's several Nobel Prizes that, were given to this field, and, it still keeps generating very interesting ideas. So, so that's, that's kind of general historical setting for where we are today. So what is the basic physics of all this? The basic physics is that you have these electrons in 2 dimensions, and they are strongly correlated, and as a result of these strong quantum mechanical correlations, they form these topological quantum fluids. And so these are interesting examples of quantum fluids where actually the bulk of the system is perfectly boring, so it's like a bulk insulator, but you have these interesting edge channels. So there's stuff going on at the boundary of the system, where these, the particles in the system can propagate, okay? And these edge channels, they are, some version of a Luttinger liquid. So there's a lot of interesting physics going on there. And one interesting aspect of all this is topological. the fact that, you know, these Z channels are extremely robust. So if there are some kind of impurities there, the Z channel essentially do not care about these impurities, that they can just go around these things. Okay, and you know, so as I said, in these kind of systems, the electrons basically, you know, change their identity and they become a new kind of particle, these anion particles. And as I mentioned, you know, the unique aspect of these particles is the statistical property. So when you take two of these particles around each other, so if you imagine, you know, as time goes on, you're adiabatically exchanging the coordinates of these two particles, your original wave function and your final wave function, when you swap these coordinates, could be related by some general complex phase, or even something more complicated can happen if you have these non-abelian states. But basically, the final state is not, you know, just plus or minus the initial state as you would have with fermions or bosons.
And Z1 and Z2 are meant to be positions on the boundary.
No, these are actually the excitations in the bulk of this system. Okay. So there's this bulk insulator, and you can think of it as being composed of these excitations. And when you take these excitations around each other, you get this non-trivial phase factor. So it's in a bulk. Okay, so that's the idea of fractional statistics. And also, like, you can measure charge of these things, these new particles, and it turns out that it's like a fraction of electron charge. So all this is basically manifestation of strong correlation in this system. So the identity of the original electron is completely lost because, you know, you don't have particles with integral charge. You just get these fractionally charged particles, and they also have weird statistical properties. So that's why these fluids are quite unusual. Okay, so what does the energy spectrum of this system look like? So here is an example of a spectrum which you can compute on a computer if you do like exact danglisation or something like that. So you take these electrons. I will tell a bit more about the precise model later on. But basically, the main features of the spectrum is that you have a ground state, which is at zero momentum. So this is momentum here versus energy versus momentum, right? So the ground state has exactly zero momentum. And well, that's the lowest energy state, right? So we measure energies relative to that ground state here. And because it has zero momentum, it means that it doesn't break translational symmetry. So the ground state is not a crystal or something like that, which you might expect in a classical system, for example. And then, you know, there's a very interesting excitation spectrum, which, as you see here, is fully gapped. So there's a gap on the order of whatever, 0.5 in these units. And so all the other excited states are above that gap. And they're not just some, you know, randomly put together some states, but they form this interesting collective mode. And I will actually talk quite a lot about this mode. Okay, and this is just an example for one of these fractional quantum Hall states, the 1/3 Laplace state, but all of them look essentially like this. So all of them will have a ground state with zero momentum, so it's a liquid state, and then there will be a gapped spectrum, okay? So that's pretty generic behavior. Now, what is actually there that's left to understand about all this, right? So if you remembered my timeline on the first slide, people have been working on this for about, you know, 3 to 4 decades now. So, you know, especially if you're a young person, you will probably ask yourself, well, you know, if I want to work on this, why should I do that? What's interesting about this? What's there left to understand? And I think the answer is actually pretty optimistic. So essentially, almost anything that extends beyond strictly ground state properties is pretty much not understood here, okay? So for example, some questions that naturally appear is, for example, why is there this gap here? Why is, you know, the spectrum gapped? So that's, you know, still kind of open question, especially if you're kind of rigorously inclined and you like to solve, you know, exactly diagonalized models like integrable models or something like that. Then the question such as, what is the Lagrangian for the system? what is some kind of effective Lagrangian that describes this physics. We still don't have that, okay? So people are still debating what is actually the correct Lagrangian to use here.
Sorry, when you wrote neutral, what was specific about that? These are charged excitations.
Right. So there could be different kinds of gaps. So they're usually in solid-state physics, we talk about the neutral and the charge gap. So a charge gap would be like, it would be a gap when you add a certain number of these excitations, right? So you change the magnetic flux, and then you get a bunch of these excitations extra in your system on top of the ground state. And then, if there is a gap to creating these extra excitations, that would be a charge gap. But the gap that we see in this plot here, so this is what's called the neutral gap, because we are staying exactly at the right magnetic field such that we are at the center of this fractional Quang-Hall plateau. So there is a perfect commensurability between electron number and the number of flux quanta. And so in that sense, the system is charge neutral, but there is still a gap in this excitation spectrum. And the origin of that gap still remains to be understood. Okay, and the final question I have here is related to what is the bulk dynamics of the system. So if you perturb these systems somehow, what kind of dynamics are they going to have? Can you predict that and so on? So that's another thing we don't generally understand how to do. And of course, that's a question that extends beyond the ground state properties. So all of these questions are in one way or the other related to this collective mode. So they go back to this collective mode that I mentioned. And that collective mode has a special name. It's called magnetoroton, or GMP mode, which stands for Gerwin McDonald Platzman, because they are the ones who first proposed a variation of description for this mode. And how should you think about this mode? Well, you should think about it exactly as the analog of the roton in liquid helium. So in helium-4, as you see here, there is a similar kind of collective excitation, which was, of course, first described by Feynman and then other people after him. So it's exactly similar. The character of the modes in helium and in Quang-Hall systems is very much similar. So they're both some kind of collective, like a density wave type excitation on top of your ground state. So they're not like individual, charged excitations or something like this, but they're really like a kind of, collective density wave on top of your ground state. So you have like a liquid ground state, and then you have some kind of, coherent wave on top of that liquid. Okay, and that's this excitation. And the main difference is that, of course, in the Quang-Hall system, the mode is gapped, right? So there's a gap here, whereas in liquid helium, the mode in principle is gapless. So, it's like proportional to momentum or something, like momentum square or whatever. Okay, so, right, so all these questions go back to somehow to that collective mode. So there's still a lot of mystery associated with this collective mode. And my talk today is also about this mode. So this is the outline of the talk. So it will be basically in two parts. So first I will tell you about a certain kind of quench that we use to study the dynamics of these fractional Quang-Hall states, and in particular to study the dynamics of this collective mode that I just mentioned. And it will be a quench that that's associated with suddenly changing the geometry of the system. Okay, so we will do something to the system to, temper with its geometry, and then we will look at the response of this, what happens. And then in the second part, I will basically tell you how we can actually simulate that kind of quench using a quantum computer. Okay,
Can
so
I ask a question?
same physics, but in a different system. Sorry?
Can I ask a question? Okay.
Yeah.
Are these collective modes gapless?
So for me, they are always going to be gapped because.
But are they continuous within themselves?
Sorry, are they what?
For example, if I have a Goldstone mode,
Yeah.
they're massless, but
Yes.
the excitation is about the mass, there is no gap. There is a continuous spectrum. Okay?
Right. But Goldstone modes are associated with the breaking of some continuous symmetry,
But
whereas
yes. But
whereas in this kind of
system,
system, we do not break any. This is not associated with the breaking of symmetry.
but it can happen. Such a mode can happen without a spontaneous breakdown. What I'm asking is, are they similar to the Goldstone modes?
No.
Are they gapless within themselves? Is it a continuous spectrum?
Yes.
It is a continuous spectrum.
Yes.
Okay.
Just following up on that, your curve for the dispersion relation looks very strange in that it's dropping and constant and goes on to a constant level.
Yes. So why is that strange?
Well, the particles moving tend to have either a quadratic or for bosons or linear for fermions. Whereas here they can move faster with no additional energy.
So at large momenta where this is constant, what this says is that basically that's the energy cost to take a quasi-particle and a quasi-hole and to sort of take them very far apart from each other.
So you are not measuring the energy of the particles themselves?
Well, because it's a neutral excitation, it has to be a combination of a particle and a hole to be neutral. And at large momenta, you're basically taking these very far apart. And so the energy converges to some kind of constant value.
So you can move.
So in other words, this constant value at large momenta, it's something which is actually proportional to the charge gap just by adding a single charge excitation in a way.
But the kinetic energy of those objects should grow quadratically or linearly.
So that's a special thing about the system, that there is no kinetic energy here. So I will come to this point in a second. Okay. Any other questions? All right. So let's get started. So why is this fractional Cohen Hall effect a difficult problem? So we have some kind of two-dimensional interacting electron gas. And ideally what we want is to get to some kind of effective theory that, describes all this behavior. And, it's a two-dimensional, topological system as we know. So it should be some kind of Chern-Simons field theory of some kind. So unfortunately, to go from this microscopic electron system to that field theory is an extremely dangerous path. And, it's the path that nobody really succeeded fully, crossing up to now. So we kind of have to go in some, alternative ways to get to that theory at the end of the day. Now, how do we, as theorists, how do we think about this system? And so this is now connected to the question about kinetic energy. So first, we think about what happens with these electrons when they're completely non-interacting, right? So in this case, if we think about, Landau-Lifshitz, we have like one electron in a plane and in a perpendicular magnetic field. So that's a harmonic oscillator, right? When you do the Schrödinger equation. Schrödinger equation. That's very appropriate. So the spectrum of the harmonic oscillator, of course, is perfectly quantized, right? So you get these harmonic oscillator energy levels, which are called Landau levels in this case. And so that's a single particle solution, right? Now, because this is the spectrum of a single harmonic oscillator, there's a catch here, right? Because our original problem was two-dimensional and the spectrum is one-dimensional. So what happened here, the remaining degrees of freedom are actually making each of these levels to be massively degenerate, right? So each of these single particle levels is actually super degenerate for many electrons, right? Especially. So then if you think about putting many electrons here, you have even at the single electron level, you have degeneracy, and then you add many electrons there. So of course, it's going to be massively, massively degenerate problem. So if you think classically without interactions, this system should be something like like a metal, right? There's no reason for it to be insulated. Okay, but that's really not what these experiments see. And then, of course, what's the explanation for that? Well, the explanation are the interactions. So once we include the interactions between these electrons, that will lift this huge degeneracy and something magical will happen. Okay, so what are we interested in? We're interested in these fractional states where filling fraction is some kind of rational number, okay, less than 1. So what's the filling fraction? Filling fraction is, how many electrons you have per how many magnetic flux quanta you have in your system. So the number of flux quanta should be bigger than the actual number of electrons. So that means that there's already enough space to put all the electrons in this very lowest Landau level, right? For these fractional states. And so if all of these electrons are in the lowest Landau level, they have no kinetic energy, right? The kinetic energy is just the same constant for each one of them. So that's like there is no kinetic energy in this problem. So then what's left of our Hamiltonian? Well, it's actually just the Coulomb interaction between the electrons, as you see here. And we have to dress that with this red P, which is the global projector, which says that, these electrons should stay in the lowest Landau level. And why do we do that? Because if you remember the Landau-Lifshitz, the energy separation between these Landau levels is the cyclotron energy, and that's proportional to the magnetic field. So if magnetic field is very strong, like it is in these systems, these energies will be very far apart.
So you're dropping the ground state energy of each electron in the ground state. So you're dropping an overall constant.
Yeah. So we can measure the total energy just relative to this constant.
And that's the one that you're going to set to 0, is it?
Yeah.
Okay.
But it's literally just a constant. So
well, it grows if you add a new electron. It shifts by some infinitesimal amount.
Yes, it's a constant. It's proportional to the density, but there's no other dependence to it. So we can really treat that as a 0 of origin of energy. So then this is our Hamiltonian, and as you see, it's one of the kind of simplest Hamiltonians you will ever see in solid state physics. It's just Coulomb interaction, perfectly classical, and then what makes it quantum mechanical is this P, okay, this projection to this lowest Landau level, okay? And that's the universal Hamiltonian for all this physics. It's where all this physics comes from, okay? P gives it quantum mechanics, okay? Without P, it's just like, perfectly boring classical type Coulomb energy. Okay, so if you're maybe familiar with things like Hubbard model, which, is one of the favorite models for solid state physics, there are some similarities between this and the Hubbard model. So in the Hubbard model, it's a little bit different because we have both the kinetic energy and the potential energy, right? So we have some kind of lattice system, and then the electrons can hop with some amplitude t between nearest neighbor sites, and there can be some, on-site potential energy, right? So that's a lattice system, and the interesting physics comes from the interplay of this kinetic term and the potential term, and they do not commute with one another, so that's where interesting physics comes from. Now, the fractional Helmholtz system is different from this because we model it as a continuum system, so there isn't really like a fixed lattice where these electrons have to sit. It's really like a continuous plane. But there is no kinetic energy, right? So there is nothing in the Hamiltonian which is, like a simple band structure type, kinetic energy. Instead, what makes it interesting quantum mechanically, as I said, is this projector P, right? That's where all the quantum dynamics comes in. And the other important difference with respect to the Hubbard model is that these electrons, they live in a non-commutative plane. So if you think about their coordinates x and y, they actually do not commute with one another. And the reason for that is, again, this projection P. So once you enforce this projection, you're kind of getting rid of, part of the degrees of freedom, and that turns your coordinates x and y into operators that have this commutation relation x and y is something like I times LB square, and LB is the unit of length here, which is the magnetic length. So it's just some unit of length, which is proportional to the magnetic field. Okay, so in that sense, this is a non-commutative geometry in the system. Literally, the coordinates of these electrons, they do not commute.
Why does projecting into lower Landau levels make the coordinates not true?
I mean, it's a bit, that part is a little bit technical. I don't know how to explain it intuitively, but basically each coordinate of these electrons, you can view it as a there's a part of it which kind of describes the dynamics within the Landau level, and then there's another part which is like sending you between different Landau levels. So it's like it's a harmonic oscillator kind of thing. You can decompose it into ladder operators, and so you have two of them. You have one which acts here, and then the other one which moves you up the ladder. And what you're doing is you're discarding the ones that go up, because that's energetically expensive. And what's left is just these ones that do not commute anymore.
But these X and Y are translation operators, right? That's what you're saying.
These are position operators.
Okay.
Yeah. That's, position operators appropriate to this situation where you have to stay in the single Landau level. So it's a very kind of unusual setting where these electrons live. Okay? And that's why all this weird stuff happens. Okay, so that brings us to geometry here. So where is the geometry in all this? So the basic physics here is that it's kind of like Mott-Hubbard physics, right? So in Mott insulator, what happens there? So you have electrons which are pinned at some lattice sites, right? And they're basically frozen there. So there's an energy penalty for other electrons to come nearby. And it's the same thing here, except that there isn't really a lattice, but still you have electrons which kind of surround themselves with the correlation hole of certain area. And there's an energy penalty for other electrons to come into that area. Okay, so it's the same origin, physical origin of this. The incompressibility is the price you need to pay to bring another electron to this area around another electron. And the main difference with the Mott insulator is that these objects are not fixed, so they can kind of move around, and the whole thing is a liquid. It's not a crystal or something like that. So, that's a quantum fluid, and, it's gapped because there's an energy penalty, just like in the Mott insulator. Now, where's the geometry here? Well, the geometry is in the fact that this fluid is topological, so it doesn't really care about the shape of these areas surrounding an electron. So as long as the total area of the system is fixed, you're allowed to deform the shapes of these correlation holes around an electron. Okay, and that's the geometry, because these kind of transformations, they form this W infinity algebra, and this has been interesting for high energy physicists for some time. But the basic idea, as I said, physically is very simple. You have these correlation holes which have a finite area, but the shape of that is not fixed, so it can be fluctuating in principle. And the shape is described by this 2x2 metric, this GAB, which has the determinant 1. So that's because the total area should stay fixed. And you can parameterize that metric by essentially it's a 2x2 symmetric matrix, if you want, with determinant 1. And so there are two parameters which you can think of as like a stretch and the rotation. Okay, so that's how you can parameterize this simple metric that we have here. So what's going to happen?
Can you explain the origin of that? Because you're talking about it as a correlation hole, but yeah. Where is it coming from exactly?
It's coming from interaction, right? Because there's Coulomb repulsion here. So electrons, they do what.
No, I understand physically the physical picture, but I'm trying to get the mathematical picture. You're modeling it by some 2x2 matrix,
right?
Which is some local.
Yeah. So we can think of this. So basically, I can maybe highlight this on the next plot. So here's what happens with the actual spectrum of this system. Okay. So if you think about these geometric deformations. So on the left, we have the energy spectrum as functional momentum in this isotropic case, when these droplets are purely circular. And then on the right side is what happens when you deform them into some kind of elliptical shape. So now the spectrum will no longer be a function of the total momentum, magnitude of momentum, but it will be a function of momentum along x direction and momentum along y direction. So basically, if you look at this excitation, this collective mode, it will have slightly different shapes along different directions in the plane, but in, the gap will still remain. Okay, so it still remains a gapped mode. The details change, but the fundamental physics stays the same. And so this is the kind of thing that you can actually see happening on a computer. So you can just deform, you can just put in some metric by hand. For example, you can make the, let's say, the band structure or something, make it slightly anisotropic, and you will see that this is what happens with the collective mode. And you can actually predict exactly how it will change.
I'm still not, go ahead, Bal, I'll come back.
The symmetry is volume, preserve, and diffuse, leaving the boundary fixed. Am I right?
So we are talking about the bulk physics here.
Yeah. So it is volume, preserve, and diffuse, or the whole bulk, but without changing the boundary.
Well, the boundary, there's a question about the boundary theory, but yes, let's say for simplicity, it should stay the same, yes.
So that's, okay. But then it's an infinite dimensional symmetry group. So there should be, so far as I remember, there should be an infinite degeneracy of states.
Degeneracy in what sense?
Because the diffeomorphism group is infinite dimensional, and
yes.
The unitary representations are all infinite dimensional.
Yes.
So there should be an infinite degeneracy.
Well, so first of all, this kind of physics is we don't know if it's supposed to hold for the entire system or just that some low energy part of the spectrum. So in that sense, it may not, you may not have these degeneracies. I think I'm not quite sure I understand exactly what you mean, but it's definitely not the case that the spectrum is degenerate. So this is only approximate picture that holds at sufficiently low energies near the ground state.
So what is the unitary representation of the diffuse group? Here.
What are the unitary representations of this group?
On this system, on this, maybe a subspace of the Hilbert space, but what is it?
I don't know, actually.
Let me ask another question. The ground state, one knows up to factor, are functions of holomorphic functions of
yes.
complex variables.
Yes.
So there are holomorphic mappings, one can imagine, of the wave function, which changes from one holomorphic coordinate to another one. This must be related to that, but what is it?
Well, the thing is, once you start doing these deformations, like changing these droplets from circular to elliptical, then that property actually is no longer true. So the ground state is no longer holomorphic in that case. It starts to get, anti-holomorphic components as well. So
but
that
holomorphic structure may change under this action. So you may have another holomorphic structure, which is carried by the diffuse group and intertwined by the diffuse groups. Am I right or am I wrong?
Well, I don't know what the other structure would be. But the simple analytic, holomorphic polynomial that was there in the circular case is no longer holomorphic once you do these deformations.
That is correct. Okay.
Yeah.
Okay. All right.
Okay. So
can I go back to that dispersion relation, because I still don't quite understand it. It is saying that these particles that you've on your top left, that you can set them up with increase the momentum of them at no energy cost, at high momentum.
Yes.
So they start moving they can easily move with very high velocity with no input of energy.
Yeah. Well, if you want to think of them, these are eigenstates, right? So
it's your K. Your K is representing the momentum of some entity of some of these excitations.
Of eigenstates of the system, yes.
And that eigenstate can increase its energy, okay? It can increase its momentum without an increase in energy. I'm just not.
Yeah, because at some point, once you're separating further and further away,
but separating is not the issue. Separating doesn't change the momentum.
So
that's position. If you wrote down the position and you separated them with no cost and energy, that's fine. But you're writing down momentum with no cost and energy. So that's a different story.
Yeah, it is, but the momentum and position are kind of dual here. Yeah, it's a little bit, yeah. I don't know how to explain it very quickly.
Okay. Well, we can come back to it because
yeah. Okay, let me move on. I can come back maybe to this. Okay, so what are the questions I want to ask here? So I want to ask what are the dynamical signatures of this quantum geometry? And then I want to see how we can realize it in synthetic systems. So not in some solid state material, but something like quantum computer. Okay, so why do we want to do this? Because, you know, thinking about quantum dynamics has been very useful to study, you know, all kinds of interesting many-body systems in recent years. So, for example, people have used this idea of, you know, quenching the system to study systems that are near integrability, where they see these interesting effects like the quantum's Newton's cradle. Then people have used similar ideas to study the physics of many-body localization. And then recently in these cold atom systems, they use it to study quantum scars. So all of this is, you know, essentially you have some kind of many-body system, you're interested in its dynamics, very far from, you know, equilibrium in general. But, you know, they're strongly coupled systems, so you don't really know what it's going to do. And then you just drive them away from equilibrium by doing a quench, and you try to understand what happens there. So we're going to do exactly the same idea, except that what we're going to quench is the geometry of the system. And so how are we going to do this? So it's a very simple idea in principle. You just start from this two-dimensional system of electrons, which is in purely perpendicular magnetic field. And then you suddenly change, you know, you tilt this magnetic field by a small amount. So you can either, you know, just change the direction of the magnetic field, or you could just add a little component of the field in the plane where these electrons are. So what is this going to do? Well, in the purely perpendicular magnetic field, these correlation holes surrounding each electron are going to be, let's say, circular. And then when you tilt your magnetic field, then these correlation holes are going to deform because, you know, the field is no longer perpendicular, and these correlation holes, they will want to kind of orient themselves along the field direction. But because the electrons have to stay in 2 dimensions, that means these correlation holes will become slightly elliptical in that plane, right? But, you know, once you've tilted the magnetic field, you know, the original ground state of your system is no longer an eigenstate of the new problem. So there will be some dynamics going on. And this metric that characterizes these correlation holes will become time dependent. And, you know, the question is, you know, how do you, you know, what are the equations of motion for that metric? So what are the equations of motion for these parameters that describe the metric, this stretching and the rotation angle? So that's the main question here. That's what we would like to do. But, you know, the problem is that, you know, we're still talking about a very complicated system here. We have long-range Coulomb interactions, so it's not easy to describe, and especially not to solve this. Okay, so how are we going to approach this problem? So we're going to try to simplify it as much as we can. And the idea is you will take this system, put it on a cylinder. So that's like a 2-dimensional geometry, but then you will stretch that cylinder to kind of make it very, very long. Okay, so why do we do this? Because once you stretch this cylinder, it will kind of chop off the tail of Coulomb interaction. So it will effectively make the interaction very short range. And so what's the reason for that? Well, if you think about this limit where the cylinder is very narrow, in that limit, you have these single electron states, which are the Landau level states, and they are kind of like Gaussians, localized like a Gaussian along the axis of the cylinder. And once you know, if you make the cylinder circumference very small, what that's going to do is it will shift these Gaussians very far from each other. And if you think about Coulomb interaction, it's basically a scattering process which tries to take 2 electrons in some of these orbitals, and it tries to move them to other orbitals further away, or vice versa. So if these orbitals are very far from each other, these long-range hopping processes will become very expensive. So, a process like the second one, where you take 2 neighboring electrons and you try to move them 2 orbitals further out, that becomes very suppressed compared to the first process where you just hop to nearest neighbor orbitals. Okay, so in this sense, making the cylinder thinner and thinner basically truncates the Coulomb interaction. So it's a natural way to sort of regularize this long-range potential that we have. So in this limit, when the cylinder is quite narrow, what you do is actually you can approximate your Hamiltonian by a very simple kind of quasi-one-dimensional electron chain. So that's the full Hamiltonian in this thin cylinder limit. And you don't need to know the details of this Hamiltonian, but the rough structure is basically there's a term that looks like C dagger, CC, where these are the kind of standard creation annihilation operators for electrons. And this is the hopping process that we have on the first slide. So just 2 nearest neighbor electrons, they hop 1 position, 1 orbital outwards. So that's this last term in this Hamiltonian. And apart from that, the rest are just some density type terms. So they are kind of classical terms, just some energy penalties for nearest neighbor electrons. So neighbor electrons to be in neighboring orbitals, then orbitals separated by 1 site in the middle, and then separated by 2 sites in the middle. And these coefficients V10, V20, and so on, they're just some parameters that derive from the Coulomb interaction. So there are some numbers here.
Where is the quasi-1D?
Formally, it is 1D. Yes, formally it is a 1D chain, and that's actually going to be important because it will give us a way to write this as a kind of spin 1D model, which we can then easily simulate. And it turns out that actually this is mappable to a particular kind of spin model, which is called PXP spin model, for those who know about this. Anyway, so that's our Hamiltonian in this limit. Now the question is, do we still have some interesting physics here, or did we simplify it too much, right? Because the original system was kind of 2-dimensional, so we've thrown a lot of stuff to actually get to this point.
Can I ask a question?
Yeah.
What happened to the metric? It's gone. So
the metric will enter in these coefficients here. So it's in these V21 and so on.
So again, my question would be, how does the diffuse group act on this Hamiltonian?
How does what?
Originally, you had a volume preserving diffuse, namely determinant of the metric was fixed.
Yes.
So
yes.
one can imagine volume preserving diffuse. Okay.
Yeah.
How does it act on this edge? Well,
I mean, you can see basically what these V12 are. I mean, formally, they're something like Gaussians in the so it's like e to the minus 2 pi over L square, where L is the circumference, and then there's some other factors, and then the metric enters basically that in that argument of the Gaussian. So
okay.
I mean, we can look up the exact expressions, but it's not really essential for the time being. Okay. It enters these factors here. So now what we want to do is we want to see how the system responds when we actually change this metric. And so this is how it responds. So what we did here, we changed this metric by suddenly stretching the system by, let's say, 20%. So we make it like 20% elliptical. And we detect, what happens with these parameters of the metric as time goes on, okay? And so here you see the data for, different numbers of electrons, and you see that there's a pretty regular dynamics happening.
You made the 20% elliptic, you mean the correlation holes or the actual geometry of the system?
So the correlation holes are described by this G, right? So G is this 2x2 metric, which in the isotropic case is just the identity matrix, right? And then we quench it to something like, 1.2 1 over 1.2.
There's some noise coming. Yeah. Okay.
Sorry?
Yeah, I think he's writing on the board.
Yeah, I was writing on the board.
We can't see, of course. But,
sorry about that.
yeah. But so can you say what you were describing again, just because we missed it?
Okay, so the metric is originally
it's a two-way.
Yeah,
can just to go back to the metric for 1 second, so I understand it a little bit better. There's a metric on this two-dimensional surface.
Yes.
Which is the between your two plates. You've changed that into a cylinder, which is fine.
Well, yeah, I mean, okay, so cylinder is normally flat, right? So the metric is just the identity matrix.
No, I mean the metric is it's cylinder topologically. I mean, flat is a different question. Flat has to do with the curvature.
And the starting point is the uniform kind of circular metric, which is just the identity, right? G is the identity.
Yes, but you are taking this to be a position-dependent metric.
No, I will take it to be uniform throughout the system. So I don't want it to complicate too much to make it position-dependent, although I could in theory.
But you are thinking of just these Q's. This is the two-dimensional metric of the plane.
Yeah.
And you want to change that metric. I thought you wanted to change it in these local patches.
No, I mean, I could if I wanted, but I don't have to. I could say my system is fully uniform, so I'm just going to change it uniformly throughout the whole system.
Okay.
So all of these droplets will have identical shape if you want, but it will not be circular anymore.
The system is not 2, it's 2 plus 1. There is
2 plus 1, yeah. He's static. I think he's dealing with the same things as being static.
Yes, I'm just instantaneously changing the metric from being identity matrix to being like diagonal matrix, but not with ones on the diagonal, but some other numbers.
Okay.
Okay. So.
But the diffeomorphism group was infinite dimensional, is what Bal is pointing out, that there's an infinite dimensional action on this two-dimensional and this two-dimensional object. You are parameterizing that two-dimensional one by just doing some very restricted Q and phi deformations.
I mean, I could consider all kinds of scenarios, but let me just consider the very simplest one.
Yeah, so you're taking a two-parameter family of deformations of this, which is a subgroup of the diffeomorphism group, which is what Bal was asking earlier. That subgroup is the one that's interesting to you. Now, can you tell us a little bit more about what that subgroup is?
No.
Okay.
No, I don't know. I don't know at that level what it is. I can tell you physically.
You didn't write down the 2x2 matrix for us, so it's difficult.
Okay, well, the matrix is very simple. So as I said, it was the identity matrix on the left-hand side, right? And on the right-hand side, let's say it's a diagonal matrix, 2x2. You have, something like 1.2 is the first entry, and the second entry is like 1 over 1.2. So just 2 different entries on the diagonal.
Oh, it's just you're only changing the diagonal of this.
Yeah.
Okay.
For simplicity, that's the the most naive thing you can do. Yeah. Okay, so we do that.
Then I know what the subgroup is. Okay. All right. Go ahead.
So we do that, and still there is some kind of non-trivial dynamics going on here, because as you see, Q and phi now start to evolve in time. But the behavior is pretty regular. So Q looks like some kind of harmonic motion, and phi is this kind of piecewise linear function. Okay, so how do we interpret this? Well, there's actually a field theory that was proposed by these guys in a recent paper, which is based on the idea that what we are doing here, we are changing this extrinsic metric that describes the system, and then the system has its own kind of internal metric, which is then coupled with this one. And so this so-called bimetric theory, it's not biometric, it should be biometric. Sorry about that. Although biometric also sounds kind of nice. But it's bimetric because of these two metrics, right? One, which is the external one, which we modulate. That's the one I talked about that I'm changing. And then there's the actual metric of the system, which is trying to kind of align with this external one.
But the one of the system is presumably just the pullback of the external metric.
Yeah, that was the one we are imposing externally. And then we're asking the question, what is the internal one of the system doing?
And but it is strictly the pullback of the external one.
What do you mean by the pullback?
Well, that you induce the metric on the surface from the embedding metric.
Well, no, that's the interesting thing about this, because there's some kind of intrinsic metric that characterizes the system, and it's not trivially equal to what you're imposing on it. So what the system is going to do, it's going to kind of energetically choose its own metric, which is somehow most compatible with, you know, this many body system and the, you know, what you impose externally.
Okay.
It's not trivially just following what you tell it to do. It's a kind of, it has a mind of its own, you know.
Can I ask, this Gromov? Gromov is a mathematician?
No, he's a physicist.
It's not the Gromov-Witten Gromov, somebody else.
Well, there might be another Gromov. It's a common name.
Okay.
Yeah. It means like lightning in Russian. So it's yeah.
The mathematician is Mikhail.
So the mind of this, what this metric wants to do, is actually given by these equations here. So, you know, these are differential equations for the Q and phi, and A is the parameter, you know, that's by how much you're changing this metric. So A is that's what you impose externally, and, you know, omega is just some kind of frequency unit here. And gamma is the gap of this collective mode. Okay, because these equations, they describe the time evolution of this, you know, collective mode in the long wavelength limit. Okay, so this is, as you see, it's a highly nonlinear system, right? It has all these hyperbolic functions here. But the surprising thing is, you know, if you linearize this and solve, you get, you know, the beautiful fit to this equation, which is kind of essentially harmonic. So even though you have this highly nonlinear equation, the dynamics actually ends up being pretty much harmonic. Which is kind of surprising. It's not obvious that it should be doing that. So why is it doing that? Well, physics-wise, the reason why it's doing that is because this quench is actually a very special one. So it's doing something really special to the system, and you can characterize that by studying like a dynamical spectral function, which I'm not going to give you all the details what it is, but it's essentially like something like a dynamical structure factor that people measure in steady state physics, which is you take your ground state, you act on it with some operator, and then you ask the question, how is that state supported over the energy eigenstates of your system? And the operator that you choose should be something that's relevant to the quench that you're doing. In this case, it's an operator that somehow describes this collective mode that I talked about.
Can I ask a question? Yeah. Suppose I take a photon, electromagnetism, and I put it on this system. Which metric, let's say, coupled to, how does it propagate in this system with two metrics? Because the metric involves the propagation, Maxwell equations involve the metric.
Well, so we'll have to think about how to model that, because, you know, photon is not like it's not like a natural excitation in the system, right?
But it is there. Experimentally, it is there, no?
Well, I mean, you mean like if you shine a light on it or something like that.
Scattering. I try to do a scattering against the Hall system. Okay.
Yeah, but it will like if you think about that as like a density, like a density operator acting on the ground state. This is what you usually do when you do optical experiment in the system. That will be roughly like this. Quadrupolar excitation. So it will have roughly it will be like a spin 2 in this case.
I am not very clear. What happens to things like Gauss law? I don't understand.
Like Gauss law?
Which is very fundamental to electromagnetism. There are two metrics, but the Gauss law involves the metric. So what is happening?
I don't know. The question is about the Gauss law. What happens to the Gauss law? I'm not sure about that question.
Okay.
I think I might have to proceed.
Maybe Denjo has a comment. I don't know.
Any other questions?
I don't know, well, but the question you're asking has to do with the overall three-dimensional or 3 plus 1 dimensional space-time. So I'm not quite sure about the restriction of it to this surface.
No, the metric is this metric that is a bimetric theory in space-time. One can extend each metric tensor with time dt, and you get a space-time metric. But there are two metrics. So if I try coupling f mu nu to this, you will get the inverse of the metric in the kinetic energy term, and that will affect the motion of the photon in the system.
Yeah, but the photon doesn't necessarily see this metric as clearly as you think, because this is ignoring the space between some of those excitations, and I'm not sure what's going on there. I think you're asking a very complicated question.
Okay, the reason I'm asking is a system not similar, but maybe connected, involving volume preserving diffuse, was considered for helium-3 by Regge and Rossetti long ago. Okay, some of you may know these results, and they have discussed what are the possible excitations in helium-3 defects. So that is the issue they were. So I was wondering whether that work has a resonance here. I don't know, but
not to my mind. But maybe we should keep on because we're running a bit out of time.
Okay.
So the point of this spectral function was to say that there is an operator for which, when you act on it with a ground state and you look at its support on the energy spectrum, it's a very sharply peaked function, right? So in that sense, you're exciting not arbitrary eigenstates, energy eigenstates in your system, but just ones that are situated, in the spectrum around a certain energy. And so that energy that you see here, so that peak is precisely at the energy which corresponds to this collective mode where, where it hits, where it goes in the long wavelength limit. So what this quench really does is that it probes this collective mode, which people sometimes call the graviton excitation in the system. And the reason why they call it graviton is because it's described by this emergent many-body metric, and it carries spin 2. So it has this quadrupolar structure. It has angular momentum 2 if you put this thing on a sphere. So basically what we see here is the dynamics of that graviton excitation when you've suddenly changed the metric by a certain amount. Okay, so that was the main message here. We can do this geometry quench, and we can excite this collective mode. And using these equations here, we can predict with very high accuracy how that collective mode changes in time. So I should add that the fits to this is the solution to these equations, but the actual data here is obtained just from microscopic simulations of electrons. Okay, so we really see really beautiful agreement with this effective theory, which is a much more simplified version of the whole story. Okay, so just to tell you a little bit briefly, I don't want to spend much time on the second part, but just to give you a main idea what we tried to do in the second part. So basically what we tried to do was to start from this system of electrons that I just talked about, and to write it as some kind of spin model to basically simulate it on something like a quantum computer. And so the way we do that, this slide has a lot of technical details, but the main point is that we can rewrite this Hamiltonian that we've seen as some kind of spin model, and that model is called PXP model. So it's like a linear spin chain where on each side you have a Pauli X matrix. So X is just a Pauli matrix. But then on the neighboring sides, you have this P matrix, which is like a projector matrix. And so this kind of model is called PXP model, and people study it a lot because it's related to these cold atom systems in the Rydberg blockade. So the dominant, term of this Hamiltonian, this hopping here, is that PXP term. You can, exactly rewrite it like that. And then these diagonal terms, they just become some other diagonal terms in the spin problem. So this is at this level, it's one-to-one mapping between the two. Okay, so we don't need to go through these details. So we have a mapping of this electronic problem on this thin cylinder in terms of some kind of spin model. And this spin model is, in principle, is something you can easily do, simulate on a quantum computer or any kind of machine like that. So how do you do that? Well, the first thing you could do is to just, you just take this Hamiltonian, right? And, you want to simulate some time evolution with this Hamiltonian on a quantum computer. So how do you do that? Well, you do trotterization, right? You have your time evolution operator, Schrödinger time evolution operator. You split the, time into very small steps, and then you treat the terms as commuting, and you construct your approximate evolution operator in terms of quantum gates and stuff. But the problem with this is that that approach fails on any of the kind of machines that you have right now, because you need a lot of these so-called C0 gates, which are the entangling gates. And these current quantum computers are pretty bad in, implementing these gates. So, here you see a comparison. This is your ED result. That's exact diagonalization, what you're supposed to get. So these are the same kind of oscillations that we've seen previously, and that's the exact result. So this is here, this is like, you don't see, but it's something like a density operator. So you're measuring the, projection of spin on a given site, and you should see this nice oscillation. But actually what you see on the actual device is, something which is quite off. So it doesn't really match what you're supposed to be getting. So bottom line, trotterization fails, right? It should work in principle, but you can't, do this simple thing on real quantum computers. And so we found a way to circumvent this, which I'm not going into details now. The way you can circumvent this is by doing, some variational quantum optimization approach, where you don't actually do the trotterization, you are approximating at each time. You have some completely different kind of circuit which better approximates your state and which requires fewer of these complicated gates. So that's called variational VQE or something like this in that community. So doing that, using that variational approach, you get much better results, and that's how they look. So this is with like 5 qubits, which is like electron system with 15 flux quanta. And so we measured here different things, like this is the occupation of a certain orbital in the system. This is some kind of next nearest neighbor correlation function. And this is some overlap of your time-dependent state with the particular basis state. So in all of these cases, you see that this is the exact result. That's the oscillation you're expecting to see. And then, the rest, those are the results from the actual quantum device. So at least, they reasonably well capture what you're supposed to be seeing. So the ED is this green line, and then this is the dots are the actual hardware, quantum hardware. So we did this with 5 qubits on IBM, and well, at that point, it was the best result we could get. In principle, the protocol that we have for simulating this is fully kind of scalable, so you could easily go to bigger numbers of qubits, not stick with 5, but you will still run into problems with gates being of limited quality. So if you really try to go to bigger systems, at this point you might not be able to find really good results.
Is it specific to the PXP?
So this is not exactly PXP model. This is PXP plus some diagonal terms that you see here. So that's the actual model we have to simulate here. So it's PXP plus these local terms, but these are like classical terms, and so they're not really important. They do not, the main problems do not come from those terms. The main problems come from PXP, which requires these C0 gates. So the mapping between this and this is, it's not very general. I mean, if you had a different kind of Hamiltonian, you would have to sit down and really work out the mapping. So it's not general in that sense. But the good thing is that if we change the metric, right? I told you that the metric is hidden in these coefficients. So the metric does not spoil this. If you change the metric, you're just changing these coefficients. So that's just some parameter change in this. The mapping stays the same. So there's no problem there. So you can do any kind of quenches you like in this particular system if they're related to this geometry.
Why use a quantum computer rather than some simulator like the Rieber-Garten chain or something like that?
Well, because I mean this one we can run on our own, right? I don't have a lab with Rieber-Gartens where I could run these things on my own. And even if I did have a lab, I wouldn't know how to run it on my own. This one you can just kind of sit down and write it on your computer and send it, and you get the results. So. But in principle, the whole protocol is just defined in terms of these fundamental gates, so it's very easy to do on any kind of platform that worked out what the gates are for their system. And I'm sure they all have, they know exactly how to implement the standard gates no matter what platform it is. So,
quick question.
Yeah.
When do you optimize the gaps? When you optimize these angles?
So what you do, I didn't talk about this, but basically, in order to circumvent the problems of this trotterization, you write some kind of ansatz state, which has a form that looks like that, and then at each point in time, you optimize let's say the overlap of the exact state at that time with this variational state. So you optimize over these parameters of the variational state to get the best overlap with the exact time state, with the exact state at a given time. And this you do on a small system where you can do exact time evolution. But it turns out that these angles, they have really good scaling with system size. So you can use the angles from small system even in a bigger system.
One set of angles.
The set of angles is pretty much universal, as you see here. They have very smooth time dependence, and they change very little with different system sizes. So essentially, you just find them once and for all, and then you can use them. So in that sense, it's pretty good. It's classically optimized, but you can do it on a small system, and you can still use the numbers for bigger systems after that. Okay, all right. So basically, I think I probably want to stop here. Let me just highlight one other interesting thing. Before I conclude. So recently we asked the question, what happens if you do this kind of quench, not in this 1/3 Laflin state that I may talk about, but if you go to some other states, and there we found that you can get multiple frequencies in these oscillations. So in the results for Laflin state, you've seen that it was like a perfect harmonic oscillation, so one single frequency. But when we looked at some other states, at different filling fraction, we find that it could be like two groups of two different frequencies at least. And we interpreted that basically as related to these partons, which is an old idea about, it goes back to high energy physics, but then it was also used in fractional quantum Hall effect, where the idea is that you're physically really chopping an electron into smaller objects, and then you use that to write the wave function describing your system and then calculating everything else from that. And the interesting thing about fractional quantum Hall effect is that so far there wasn't any real evidence that that's what happens. People just use that idea of chopping the electron as a kind of mathematical trick to write down some wave functions and to get some kind of variational ideas. But when we did this quench, we found that these multiple frequencies that you see in those quenches could only be, well, to the best of our knowledge, they could only be explained by this idea of partons. And so that's, you can read about that in this very recent preprint. And let me just show you the results. So basically that's, one spectrum of one of these states. And that's this is quantum fidelity. So just the overlap of the initial state with the time evolved state. And it has some dynamics that looks like this for two different system sizes. And when you do the fast Fourier transform on this signal, you see that there's like two groups of frequencies here, okay? Whereas in the Laplane case, there was just a single dominant peak. Here we have at least two of these peaks, and we were able to actually write down like a variational wave function for these, based on this parton construction for the collective modes, and we found that there are two modes. The one with the lower one is this standard collective mode that I told you about in the Laplane state, this GMP, Gervin-McDonald-Platzman collective mode. And then from the parton picture, we got this additional mode, which is at higher energies, and that's the one that corresponds to the additional peak in this geometric quench dynamics. So it gives additional frequency to the quench dynamics, and so we think that this sort of proves that, you know, these particles, that this division of the electron into these partons is actually, there's something real to it. It's not just a mathematical trick, but actually, you know, if you do this particular experiment, you will see the signatures of that. And it's funny because it's kind of really analogous to the way you think about quarks, right? Quarks are also like when you're splitting, when you're splitting these kind of elementary particles, then the only way to see quarks is to really dump a huge amount of energy into your system, right? And then you see at very high energies, you see some signature of these quarks. So we are doing exactly the same thing here. If we dump a huge amount of energy such that we probe, we reach this higher collective modes, then we start to see signatures of these partons. But if we don't dump enough energy, we might only be seeing the lower mode, which can also be explained in alternative theories. So this was kind of nice. And, you know, of course, what remains to be seen is, you know, if experimentalists can really do this thing somehow in experiment and prove that indeed there are these two modes. Okay, so basically time to conclude. So I've told you about this idea of geometric quench, which is when you take these fractional Hall states and you suddenly change their geometry. And, you know, then they produce some kind of interesting many-body dynamics, which we've understood in this biometric field theory, and also we reproduced in numerical simulations. And we can do that either, you know, on classical computers, or we now also know how to do it in principle on these quantum computers. And there's lots of interesting questions that, you know, still remain to be understood about this, like, you know, these additional collective modes that are associated with these partons. That's something that's quite exciting. Then for these non-abelian states, like the Moore-Reed state, if you look at their excitation spectrum, it also has multiple collective modes. One mode is like still like the GMP collective mode, but there's an additional collective mode, which in this case is related to the non-abelian statistics. So it's kind of like adding it, because this is in this Moore-Reed 5-half state, which is some kind of superconductor. So the way you get this additional collective mode is when you have an unpaired electron in your system. So in this sense, it's called, it's like a neutral fermion. It's something that appears only in these paired states that have some kind of superconducting physics. And so if you were, the question is, can you do some kind of quench like what I described to actually see the presence of that other mode? And that's something that's not really understood. And then there are also other kind of systems, these nematic systems, where the collective mode is actually supposed to become gapless due to some other types of effects. And in these kind of systems, of course, it would also be interesting to study these quenches, because since the mode is becoming gapless, then the whole dynamical response will also be very different from the gapped states. So there's, you know, there's lots of things to think about when you move away from the ground state. That was the kind of one big message of this talk. And that's it. So thank you for your attention. And just to flash out lots of people who were involved in doing various aspects of this. In particular, the first three guys that, you know, we've done several papers on these things related to field theory, partons, and so on. And then these guys were involved in the quantum simulation aspects in IBM. All right, so sorry for running over time, but I guess there were lots of questions, so it's okay.
Well, thank you very much. I think Gian Domenico is going to manage the things there, are you? From the audience. Are there other questions? Just
I want to ask,
please,
it was a very stimulating talk, by the way. But I want to ask, you're getting an even denominator state, this neutral fermion.
Yeah.
Those are supposed to be very weak, no? Very rare.
We have something.
Sorry. I have to read it. Okay.
So the question was about more read states.
You're getting even denominator states from what I see from your middle graph.
Yes. I mean, so is it rare? You mean, well, many people believe that it exists in experiments, so it's not...
No, I know it exists, but they are supposedly very weak. The excitation.
Oh, no, actually, they are not that weak. If you look at that Landau level where this state is realized, actually it's the most stable fractional composed state in that Landau level. It's more stable than the Laffin state in that Landau level.
Okay.
That's maybe a common misconception about this state. I mean, it is of course weaker than the states in the lowest Landau level, but in that Landau level, it's pretty strong state. And also the experiments in graphene have really increased the gap of that state quite a lot.
Okay.
So now the gaps of this state are on the order of Kelvin.
So let me ask again, in your IBM computer, there's somebody called Santiago. What is that?
Well, these are just different, the different processors that they have. They give them these weird names like, Santiago.
Okay, fine.
Yeah, so that's the name of that particular processor that was used. I'm not sure if it's still available, but...
All right. Okay, I just didn't know.
Sorry, what was the reference Landau level that you were saying? You have the ground state and you're talking about the first excited state, is it? First excited Landau level.
You mean for this 5-half state?
Yes.
So that's the one that, that's the one that occurs. So that's the one that occurs when you take, like here we have, you take the lowest, you take this lowest Landau level.
Yes.
You completely fill it with electrons that with both up and down spin. And then there's half filling in this middle, in this what's labeled 3-half here.
Okay.
Yeah, so that's where you get that.
That's right. Okay, thanks.
Okay.
Any question here? Okay, so if there are some other questions, we can thank again the speakers. And okay, so
I will stop the recording then, just to continue.
Oh,